Okay, next we have power in a wave. How we can define power? Power can be defined as the energy transferred in unit time interval, in unit time or in unit time, in unit interval of time, in unit interval of time. And mathematically we can define it as power can be defined as energy transfer per unit time. So we represent power by this P symbol, which is equal to dE by dt, or the rate of change of energy from one point to another point is called power. We can also write this equation as, I can write this as dE over dt or dx into dx over dt, because again dx cancel with each other, so we left with d over dt. Now since wave is traveling in the x direction, okay, wave, if this is a wave in a string and this is my xy axis and this is y axis, this wave is traveling in the x direction, so this dx over dt is the velocity of the wave. So we can replace this dx by dt by this v, not by vy. Vy is basically the velocity of the particle, and the particle is always moving up and down, because if this is the particle, then this particle move up or down, or move up and down. So its velocity is vy, which is equal to dy over dt. But here dx over dt, and we know that wave is traveling in the forward direction, the x direction, so this is the velocity. Dx over dt is basically the velocity of the wave. So it means that this equation can be written as P is equal to power is equal to v velocity times dE over dt. Now we already know that dE over dt, or we can say dE over dx. Yes, this is dE over dx now. We can write P is equal to v. For this I replace v, and here we left with this term, which is dE over dx. And we know that we already did in the previous video that dE over dx, total energy per unit length, is equal to mu omega square a square cos square kx minus omega t. So using in above equation, we have the power P, which is equal to, we have v, and then we have mu omega square a square cos square kx minus omega t. Now I call this is equation number 1. Now equation 1 represents the power transmitted by the wave. This is basically the instantaneous power. By instantaneous I means the power transfer from one point to another point such that the points are very close to each other. I can say that this is the instantaneous velocity. And we consider this length dx, which is between these 2 points. We derive this relation for this situation, for this dx, and we suppose that dx is very, very small. So it means that this is the power, instantaneous power, the power transmitted from one point to another point such that these 2 points are very close to each other. Now we will calculate how much power a wave transmit during one period. Like one period of time, how much energy is transmitted, we will calculate that one. Now power transmitted during one period or one wavelength distance are in one complete cycle. This is instantaneous power. It's a power transmitted between 2 points when the points were very close to each other. Now we will calculate the power transmitted during one period we can say that during one wavelength distance, we can say that during one complete cycle, because this is one complete cycle. We can say that this is one wavelength also. This is one complete cycle. This is one period. So we will calculate the power in this one. Now, power can be defined as average power. So it's basically the average power, P average, which is equal to the area under the curve, which is P times dt divided by the base. Base is from 0 to t. So it's basically the time taken. So this is the area of the curve divided by time. And we know that P is, we already calculated the instantaneous power, which is a square omega square mu into v integral of cos square kx minus omega t into dt divided by, we have the period which is from 0 to t dt. It's basically, it's not dt, it's basically this is 0, this is pi, this is 2 pi. So it's from 0 to 2 pi. Because the full period is from 0 to 2 pi. So this will also be from 0 to 2 pi. Now I have to simplify this one. From this I will get 2 pi value. So we have a square omega square mu into v divided by 2 pi. And here we have integral from 0 to 2 pi cos square kx minus omega t to dt. And we know that cos square theta will be equal to 1 plus cos 2 theta over 2. So I replace this by this identity. So we have a square mu square a square omega square, a square omega square mu v over 2 pi, and we have 0 to 2 pi, and we have 1 plus cos 2 into kx minus omega t divided by 2 dt. This is equal to a square omega square mu v over 2 pi. I will separately apply this integral to this part and this part separately. So I will keep this 2 outside of the integral. So this is basically 4 pi. So here we left with integral from 0 to 2 pi dt plus integral from 0 to 2 pi cos 2 kx minus omega t into dt. If I solve this integral and put the limit, then this will become 0, because from this we get sine, and sine 0 is 0 and sine 2 pi is also 0. So this term is automatically become 0. So here we left with only this one, and from this if I integrate it and put the limit, I get 2 pi. So we have a square omega square mu v over 4 pi times 2 pi. So it means that the average power, P average, this is basically P average, will be equal to 2 cancel with this. So we have 2 pi cancel with pi. So we have a square omega square mu v over 2. This is the total power transmitted during one period or during one wavelength distance or during one cycle. Next we will calculate the intensity. And we know that it is the intensity of wave. Intensity of wave. Intensity can be defined as energy transmitted per unit time, energy transmitted per unit area, and unit time. Suppose we have energy which I represented by this U. This is the flow of energy. Now here we take a small square or small square of area A. This is area A. Area which I call A, which is per meter square, and this is the flow of energy. Now we take a unit area which is 1 meter square, place this unit area perpendicular to the flow of this energy. The energy transmitted through this unit area, the energy transmitted, and I save that energy, then that energy is called intensity. Mathematically we can define intensity I is energy transmitted per unit area per unit time. Here this is the area of the surface through which this energy passes. Now we define intensity as energy per unit time, energy transferred from one point to another point, power. So it means that intensity can be defined as E over T as power divided by area. And we know that power is given by this relation. So intensity will be equal to A square omega square mu v over A. I call this area small a, not capital A, because I already introduced the sample A for the maximum amplitude or the displacement. So that's why for differentiation I just call this area as small a. And we have 2 also there, so it's basically 2a. Now we consider the string to be like this. It has some volume, it has some area, and also it has some length. I consider the string to be length L, and I call its area A, because energy is transmitted transmitted from one point to another point through this string with area A. Its mass is m and its linear mass density is mu. We can define mu as mass per unit length. Now if I use this relation in above equation, we get in this equation I is equal to a square omega square. Instead of mu I will put m over L. So this is velocity, okay. This small v is velocity over 2AL. Now here area is A, length is L, so volume I represented by this capital V, which is equal to length times area. So it means that this term basically gives us this volume. So I can replace this AL by V. So we have the intensity, which is equal to A square omega square, and we have mass times velocity of the wave divided by 2 times volume of the string. Now I can write this equation is A square omega square over 2, and I put it like this, m over v times this small v. Now mass per unit volume. Mass per unit volume is called volume density, and it is represented by this rho. This is equal to mass per unit volume. So I replace this factor by this rho. So we have the intensity I, which is equal to A square omega square. This is equal to rho times v over 2. This is the velocity of the wave. So this is the formula for the intensity of wave. It's equal to A square omega square rho v over 2. I can write intensity. The final expression is I is equal to A square omega square rho v over 2. So this is the formula for the intensity of wave. So this is the end of this topic. In the next topic we will move to another concept, which is called the superposition principle. Thank you.